All right, guys, welcome back. What this video is going to do is two things. It's going to provide like a 5 to 10 minute summary of everything we've learned in 9.1 through 9.3. And then we're going to go through a couple examples, seeing how we solve problems in 9.3. Now, if you want to just listen along because you're like, man, I feel pretty good about 9.1, 9.2, and 9.3, go for it. But if you're like, I feel iffy about different parts, especially if you ask me to look at a problem and say, hey, this is a 9.1 type problem or this is a 9.3, then I would recommend writing this down. So 9.1, we introduced the following formula. X bar minus E is less than mu is less than X bar plus E. And what was the whole idea of 9.1? Well, the idea is, let's say I have some population. And obviously, whatever we're measuring in that population, there is a mean, a population mean. And we think about maybe the fish in the pond to give some concrete example. It is way too complex and too difficult most of the time to actually calculate by hand the population mean. We don't have the time, money, effort, resources. I can't catch all the fish in the pond. So what we said is, well, we can take sample means, and those are a lot easier to calculate, but here's the problem. If I catch, say, 10 fish out of the pond and get their average length, and then I throw them all back, and then I catch 10 more fish, and I keep doing this process, am I going to get the sample mean every time? Well, what you're saying, well, I will get the sample mean each time, but will I get the same sample mean each time of those 10 fish? Of course not. Any of you who have fished ever in your life know that if you go catch 10 fish, throw them all back, and then catch 10 different fish, are they going to have the same sample mean? Absolutely not. What we find is each time we would draw a sample and find a sample mean, it's not the same. Therefore, our sample mean logically can be deduced that our sample mean will not equal our population mean. There is some amount of error that separates it. Okay, and what did this error come from? Two parts to it, a critical value, and then what we would call the standard error. And so our logic was, if the sample mean doesn't equal the population mean, then I can do the next best thing. I can use the sample mean to predict the population mean by using it to create a range of values I'm some degree of confident that the population mean will be between. Right? And for all those sample means that I keep drawing that are all slightly different, they'll all produce different confidence intervals. And the idea is that I can be, if I'm 90% confident, I can be 90% confident that out of all my sample means that create all these different intervals, out of all these intervals, 90% of these intervals will contain the true population mean. So what we're going to do is we're going to take a sample mean, our specific one that we draw, and we'll say I am 90% confident that using our sample mean, I am 90% confident that this confidence interval from our specific sample data will contain the true population mean. And so we use this idea of adding and subtracting some amount of error to the sample mean to come up with our confidence interval. Now that error is made up of two parts. The first part being the critical value. And because in 9.1 we're working with large samples, the idea is that because the sample size is large, it's greater than 30, the normal distribution approximates our sampling distribution, which we didn't talk a ton about, but it approximates our sampling distribution very well. The normal distribution and our sampling distribution of our sample means. What do I mean by sampling distribution? That would be if I kept taking size or samples of size 10 out of the pond and calculated the sample means, the distribution of all those sample means is normal based on matches the normal distribution based on the fact that the sample size is greater than 30. Either way, because that is true, my critical value will be found by looking at the standard normal curve. And what does the critical value tell me? What if I want to be 90% confident and the normal distribution adequately approximates my sampling distribution? Then what I can say is I can look at my normal curve and say, if I look at the standard normal curve, the critical value would tell me what two values contain 90% of the data. Since area under the curve is probability, what we can then say is that if, negative blah, 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 to blah, blah, blah contains 90% of the data, then that's how many standard deviations I need to go above and below a mean to contain 90% of the data. And that's exactly what we do. We find our critical value. It says you need to go this far above and below the mean to contain 90% of the data. And we multiply it by our standard deviation from our sampling distribution. Again, we did not spend a ton of time talking about where that came from or the theory behind it. You've heard me articulate some of it. So if you want to know more about it, let me know. Okay, so this was our general idea for 9.1 confidence intervals. My sample mean doesn't equal the population mean. So we do the next best thing. We come up with an interval that we can say with a degree of confidence, our interval based on our sample data will contain the population mean. I am 90% confident that between values blank and blank, or that my interval blank to blank will contain the population mean. And that was kind of our idea in 9.1, and we executed it and we solved it. The last part of this would be, we usually didn't know the population mean, but again, because the sample size was large, we could substitute in a sample standard deviation with no problems. So what we then do in 9.2 is we said we want to do the same thing, but now we're working with small sample sizes. And the overall idea didn't change, right? We're still taking away and adding some level of error to our sample mean to give us a range of values that we are 90, 95, 99% confident the population mean will be between. But we're working with small sample sizes. And the problem is that affects our error. Because if we use the same tactics that we did in 9.1, substituting S in for sigma, whenever, if we didn't know sigma, and using Z of C as our critical value, it turns out it doesn't produce for us the accuracy and the confidence intervals we're looking for. What do I mean by that? That means if I kept drawing samples, what would happen is if I wanted a 95% level of confidence, but my sample size is less than 30, well, all those confidence intervals, 95% of them wouldn't contain the population mean. My error would cause some flaws here. The confidence intervals wouldn't be to the degree of accuracy that I'm asking for. So instead, how do we get that degree of accuracy? Well, we no longer use the normal curve to approximate our sampling distribution, or distribution of sample means. What we would use is the t-distribution. So practically, instead of Z of C, I'm using T of C. My critical value will come from a t-distribution. Again, in this case, when we're working with small sample sizes, we never know the population standard deviation. And we still divide by the square root of our sample size. By working with the t-distribution, we're going to get our confidence intervals. Again, if I would take a bunch of different samples of the same size, calculate a bunch of sample means, create a bunch of confidence intervals. By using the t-distribution to calculate my error, what I end up doing is I get that accuracy I'm looking for. 95% of those confidence intervals will contain that population mean. So how do we calculate the critical value T of C? Well, we use this formula called inverse T. 0.5 times 1 plus our level of confidence. And then this was all based on our degrees of freedom, which again was our sample size minus 1. Because all t-distributions are different, what happens is each t-distribution is slightly different depending on the sample size, specifically the degrees of freedom which is our sample size minus 1. So again, we were able to create our confidence intervals. Life was good. Now in 9.3, what we introduce, something a little bit more off the wall. We say, hold on, we're tired of estimating the population mean. I almost wrote mu there. We want to estimate the population probability of success in a binomial distribution. Now let's back up. A binomial distribution comes from a binomial experiment. What's a binomial experiment? Well, it's the idea, really it boils down to, you have a success and a failure. You either succeed or you fail, and you're choosing some number of successes out of a total number of trials. Think about this. Let's say I have a die in my hand, and I say rolling a 3 is a success, anything else is a failure. The binomial experiment would be me saying, given that setup, me rolling a 3 is a success, not rolling a 3 is a failure on a fair die, what is the probability that out of 10 rolls, at least 4 are 3s, or no more than 2 are 3s? And we would go on and calculate that. We did that in chapter 6. But what we want to do here is, again, unlike the die example where we know the probability, the population probability of getting a 3 is 1 out of 6, we want to estimate the population probability. Think about the flu example we talked about on Friday, right? It's not ethical or practical for me to force 20,000 students at a university to get a flu shot and then expose them to the flu and see if the flu shot works, okay? Instead, what I do is I get a sample group. I find out the sample probability that the flu shot works for someone, and then I use it to estimate the population probability. Again, keeping in mind that for one sample of students, if I took another sample of the same size, that sample probability is going to change. And if we kept doing that, the sample probabilities would make a distribution, which again, is it called a sampling distribution and is the basis for what we're doing here. Point being, we'll use a sample probability to estimate the population probability. As always, we're taking away and adding some error. And we said for this section, we are going to work again with large samples, but what constitutes a large sample when you're working with probability? We talked in 7.4, if n times p, your sample size times your population probability, is bigger than 5, and your sample size times your probability of failure is greater than 5, a binomial distribution will be normal, which means a distribution of sample proportions will also be normal, and we are good to use the normal distribution as an approximation for a sampling distribution. Practically, what does that mean? It means we can use Z of C to find our critical value. Again, going back to inverse norm. Okay, now there's always a second part to finding that critical value, or to finding our error. It's the critical value, the number of standard deviations we need to go away from the mean to contain such and such amount of our data, and that is the standard error, which is the standard deviation of the sampling distribution. Again, we don't spend a ton of time talking about that, but if you'd like to know more, let me know. And it turns out that that comes out to be p hat times q hat divided by n, all square rooted. That's our standard error when working with calculating confidence intervals for proportions. P hat being the sample probability, Q hat being the population, or Q hat being the sample probability of failure, P hat being the sample probability of success. Okay, so here we are. This is our formula. Again, if you are looking back, again, this would be 9.3 in green. We covered 9.2 in blue and 9.1 in black. If you have any questions about that, make a star in your notes. If any of that's foreign, let me know so that I can help you. Now, we talked about the theory on Friday, and so now of 9.3, and I discussed it a little bit just there. Let's get into executing some examples. So how are we going to practically solve 9.3? Well, we'll run through an example here, and then if you want another example, shoot me an email and let me know. Otherwise, I think after going through this example, you'll see it's pretty straightforward and you can move into the practice. So suppose that 800 students are selected from a college that has 20,000 students and they are each given a flu shot. Then these 800 students are exposed to the flu and 600 of them do not contract it. Find an interval estimating the probability with 99% confidence that a single student selected at random from the entire population will not get the flu if they get the flu shot. So a lot going on here. But what curbs my anxiety when I'm looking at a lengthy word problem is identifying what they want me to do and writing down a formula that'll help me do it. We're supposed to find an interval estimating the probability with 99% confidence. They want a 99% confidence interval estimating a population probability. So what's our formula? P hat minus E is less than P, our population probability of success, is less than P hat plus E. Okay? Well, first things first, we got to identify P hat. And remember, P hat is calculated by taking our number of successes divided by our sample size. Well, if you look back at this example, 800 is the number of students in the sample. Again, we're using the sample probability to estimate this for the 20,000, our population. And what is our number of successes? Now, before we determine this, we have to first figure out what is a success. Well, they tell us we're supposed to find an interval estimating the probability with 99% confidence that a single student selected at random will not get the flu if they get the shot. That is the success. So what is our number of successes? Well, if we look back up here, 600 students do not contract the flu after being exposed to it. Therefore, my probability of success, or my sample probability of success, is 600 over 800, which is 0.75. And be careful. Please be careful. You got to be careful to know what a success is and what isn't. If I mistakenly said that the number of successes was 200, as in the number of people who did contract the flu after getting the flu shot, then my whole problem's going to be off. Make sure you know what a success is when you're looking for the number of successes. Well, now at this point, now that I know P hat, I have to calculate some error. But before we can do this, we got to make sure we can even solve the problem. Right? Because the normal approximation for our distribution of sample proportions cannot be normally approximated if n times p is not greater than 5 and n times q is not greater than 5. And if you've been paying attention closely, this might puzzle you because we don't know p and q. In fact, p is what we're trying to estimate. So how do we do n times p and greater than 5, n times q is greater than 5? Well, the reality is, P hat and Q hat, or P hat does not equal P. We're using it to estimate P, but they're not equal. It can be used as an estimation in the place, and you'll see why in a second. So if I use P hat and Q hat here, what I'm going to do is 800 times 0.75. Remember, Q hat's the probability of failure, so 800 times 0.25. And I just have to make sure they're both bigger than 5. Because I'm just trying to make sure they're both bigger than 5, it is fine to use P hat as an estimate for P when seeing if the binomial distribution and the distribution of sample proportions will be normal. That is an A-OK choice to make. Okay, we're just trying to see if they're bigger than 5. Clearly, with a sample size of 800, I am going to end up being greater than 5, even though the population proportion is not exactly 0.75. So we have checked that. So we know our binomial distribution is normal, which means our distribution of sample proportions is also normal. So what does that allow us to do? Well, that allows us to calculate our error. Specifically, we can find our critical value, Z of C, and multiply it by the standard error, which is P hat times Q hat divided by N. Well, I know that part of it. P hat's 0.75, Q hat is 0.25, and the sample size is 800. So now I just need my critical value. Again, we've done this a lot in 9.1. I want to be 99% confident. So we're trying to find the two values on the standard normal curve such that 99% of the data lies between them. 99% is in the middle, that means 0.5% is in each tail. So when I set up my inverse norm, remember that's area left. My first boundary, this guy right here on the left, will be 0.005 when I turn it to a decimal. And my area left of my second point will be 0.995. When you calculate this out, you get negative 2.58 and 2.58. If the values are the same, you know you did it right, which means my critical value is 2.58. Again, practically, that means you need to go 2.58 standard deviations above and below the mean on any normal curve to contain 99% of the data. And now I can calculate my error, which when I multiply that out, I end up with 0.04. I'll round it to 2 decimal places because we're working with percentages. Which, if we go all the way back to the top, means if we set up the full confidence interval, P hat 0.75 minus 0.04 is less than P. So some 0.75 plus 0.04. And what we end up with is 0.71 is less than P is less than 0.79. Now, what would this mean in the context of our problem? Well, we always have 3 parts to our explanation. Number 1, we're going to state their level of confidence. I am 99% confident. Now we're going to talk about our interval. That my interval, which is based on a specified sample, we could have gotten a slightly different interval if we got a different sample of the same size. That my interval, I'm going to put these as percentages, 71% to 79%. And the last part contains the true population probability. We can do some interpreting here in the context of the problem. I'm 99% confident that my interval 71% to 79% contains the two population probability percent, whatever you want to say. And we're making this interval for the probability that a student selected at random will not get the flu if they get the flu shot. So I am 99% confident that my interval 71 to 79% contains the true population probability of a student not contracting the flu if they get a flu shot. Again, we don't know what that true probability is. Maybe it's 75%, maybe it's 74%, maybe it's 78%. Maybe on the off chance it's not even within our interval at all. Again, we're only we are 99% confident that that true probability is in our interval. But, there is a 1%, level of, it could be outside. Our interval could be that one oddball interval where the true population probability isn't in there. But most likely it is. So we are 99% confident that our interval 71 to 79% contains the true population probability of a student not contracting the flu if they got a flu shot. Guys, thanks for watching. Let me know what questions you have.